Hi, everybody.
Hello. Hello.
All right. Okay. Any questions? Maybe a couple things. I haven't yet posted this week's homework. I'll do that this evening. And either today or tomorrow, I'll also start posting some more presentation topics. I was going to kind of transitioning into the segment of the class on measure theory integration. So the next set of topics will be on related to that. And then this section is of course deeply related to Fourier analysis. We're going to come back to Fourier series after we develop the Lebesgue integral. So there'll be more topics in the Fourier world, or explicitly inside the Fourier world towards the end of the course as well. Okay. That said, any questions before we start? Okay. All right. So it's time. So we're gonna buckle down and discuss measure and integration. We've kind of reached the point of no return where we're now at a sufficiently advanced level where we need something. We need some a more sophisticated way of understanding integration. Okay, so let's just try a little bit more just to motivate where we are and why we need to sort of start again from scratch in some sense. So why and what problems are we trying to solve? This chalk looks gigantic. What problems are we solving?
Can you share your screen?
All right. Thank you.
No problem.
I think this is going to become a daily occurrence, or a bi-weekly occurrence rather now. What problems are we solving? Are we interested in solving? Well, there are a couple, and we've already seen a major one. So, given what we did a couple lectures ago was we defined two vector spaces, so norm vector spaces. One I'll call L2 functions on the torus, and on the torus of Riemann integral functions. So this is all f t to c rather complex valued functions on the 1D torus, such that f is in R of t, and the norm on the space is, or rather maybe say the inner product, more generally, inner product L2 is 1 over 2 pi integral from minus pi to pi f of x g of x bar dx. So on the one hand we have this space, and on the other hand we have this space little L2 of z, which is just the space of all sequences, say indexed by the integers, such that this is finite, so they're square summable sequences, and the norm, sorry, the inner product between two sequences, maybe I should write it like this. This is a little L2Z inner product is defined by A and B and bar. Okay, so we defined these two spaces, and then over the course of the last couple of weeks, we defined a mapping between the two of these. So we have a mapping. Almost on the first day of class, we defined a mapping here. F that takes L2, maybe I'll write this as like just like this, R of T, into little L2 of Z, where the mapping is you take a function here and you send it to the sequence of its Fourier coefficients. So to each function, we associate a sequence of numbers, right? The Fourier coefficients of that function. So this is a mapping between two inner product spaces. And we proved, in fact, the Plancherel identity of Plancherel theorem is that it's norm preserving, this map. So the L2 norm of F is equal to the little L2 norm L2 norm of the sequence of Fourier coefficients. So then we also discussed the issue of inverting, of finding an inverse to this mapping cat. So I've written this kind of abstractly, right? We associate to each F its Fourier, the sequence of Fourier coefficients. And then the question we were trying to ask about that sequence is, can we recover back the function F from it in a meaningful way? And, you know, we did partially construct an inverse to this map for functions that are in the image, right? So can we invert this map? Can we invert this map? There's an inversion formula, in fact. So the natural choice for inverting this map is to associate to a sequence AN in little L2 Z gets sent to the corresponding Fourier series, e to the I n x, right? This is a natural choice for the inverse of this map, right? Because if I call this F inverse, then F inverse of this sequence. So if I started with so maybe if I should write like this, F inverse of F of a function F, if I start off with a Riemann integral function, associate to it its Fourier coefficient F of the sequence F hat of n, which is equal to, right, F hat of n e to the I n x for n c. And we showed that the corresponding sequence of partial sums minus F. So the question is this equal to F, right? And we showed in the sense of, like, if I think of this mapping as between this little L2 and L2, then yes, right? We showed that this goes to 0 as n goes to infinity. So yes, right? For for such functions, right? If we have a Riemann integrable function, then this we proved this theorem class ago. This inversion formula does hold for Riemann integral functions. Okay, but the problem is that this doesn't work for for this to be a true inverse. We would need I feel like I'm shouting into the computer. Sorry. for this mapping to be a true inverse, we would need this for any arbitrary sequence we picked and that square summable sequence. We would need this to make sense as a function in L2. But we saw by that's just not the case, right? There, in particular, like I guess this mapping is not onto. So there are sums, like there are sequences like this which are not the Fourier series of any Riemann integrable function, right? I mean, we saw this by like just taking the sawtooth function and chopping and throwing away half of the Fourier coefficients. Then we saw, in fact, so who proved this for? Christina proved this for us in class, that this cannot be those cannot be the Fourier coefficients of any Riemann integrable function. But yet they're square summable, right? So the map is not onto. The map F is not onto, and in particular, there's no way to we can't define such an inverse function. This does not land. This may not be in L2 of R of t, right? Okay, so this problem, this is a problem, or it's not a problem. It's just not as nice as it could be. And a natural question to ask is, can we find the natural is there a natural domain for this map with this structure? We want Plancherel theorem to hold, so we want this. We just want to have the proper domain of L2 functions, the proper class of functions on which to define this norm L2, so that this map is onto. And moreover, we showed in exercises that little L2 of Z is a Hilbert space, meaning that it's complete with respect to the little L2 metric. But on the other hand, this space is not complete. This space is not complete with respect to the L2 metric. The Riemann integrable functions is not complete with respect to the L2 metric. So we'd like to resolve this. So can we resolve the two issues? One, not complete, or maybe I should write like this: the Riemann integral functions on T not complete under the L2 metric. And two, F is not onto. Okay. So this kind of came to a head at the turn of the century, not this last century, the turn of the 20th century. Let me see one thing. I wanted to tell you the timeline. The theory of measured integration, Lebesgue's kind of seminal papers in 1902. This was resolved. Okay, so okay, so this is one big aspect, and this is why this is why we do measurement integration in this course, because this is one of the main drivers of the of of trying to of coming up with new integration theory, was trying to resolve these issues. So let me point out a few more. I really like the very beginning of your next textbook, the real analysis book, that has these four really fundamental problems with Riemann integration. These four big issues that were coming to a head around the turn of the 20th century. So this is one. Maybe I should rename these questions as to A and B. Okay, second, so limits of sequences sequences of functions. Maybe we can just even drop the torus now. Sequences of on some domain X. So say, e.g., X equals 0, 1, say the closed and bounded unit interval. So what's the problem is the following. So on the one hand, if you have a sequence of functions, of continuous functions converging uniformly, then one of the culminating theorems of your first analysis class is to show that the integrals in fact converge. The sequence of functions converges to a continuous function if they converge uniformly. And moreover, the Riemann integrals of the sequence, that sequence of numbers, converges to the integral of the limit function f. Okay, but as you also probably learned in real analysis, there are plenty of examples of sequences of functions that converge pointwise, but not uniformly. And you had no way of making sense of the limit in that case. And it's actually quite bad. So I think these kind of examples started popping up, and people were like, wait a second, we didn't think of functions like this. But in fact, and at some point we'll do this probably in the homework problem, but there exists a sequence Fn of continuous functions, each of the Fn's. Make sure I can write more cleanly. On the unit interval, such that they're bounded, so they are decreasing. So it's a decreasing sequence of functions. They're positive, bounded, decreasing, and Fn's tend to converge to a function f of x, such that f is not Riemann integrable. So there exists a sequence of functions that are, this is a nice looking sequence, right? They're bounded, they're decreasing, and they're pointwise convergent to some function. Okay, but I claim that there's an example where f is not Riemann integrable, but this is funny. This is bad, kind of, because, well, there's a clear gap in the theory, because if I then think about the integrals of these functions, right? They're all continuous, so I can make sense of all of these, right? I can make sense of each of these integrals. These exist for every n. Not only that, is a decreasing sequence, right? Since the functions are positive and decreasing, continuous, they're positive continuous functions, they're decreasing, the integral gets smaller and smaller, right? It is decreasing. Which means that the limit, and bounded below, right? This is now a sequence of numbers that's decreasing and bounded below by 0, right? Since each of these functions is non-negative. So this means that this limit exists. But and so you'd say, well, I'd like the whatever it means to integrate, so that the integral, this limit, this the what I'd want is the integral of f, the pointwise limit of these functions, to be defined as the limit as n goes to infinity fn, right? But you can show that this function that arises as the pointwise limit is not, like, you cannot make sense of the Riemann integral of it. So even though it seems very natural that this should be the definition of the limit, right? If this limit exists, why not, right? This seems like an example that we should be able to handle, right? If integration means something, but this is the limit. This is the problem with the Riemann integral. Is it this construct an example like this? I guess this kind of this type of example where it came from games played by Cantor at the end of the 19th century. But this is a significant problem, right? Like, limits end up being kind of the main object in analysis, and the Riemann integral can't make sense of such a situation. Like, there's some problem here. So I want a theory of integration that allows such a situation, that allows for such a definition, that the integral of f to be just equal to this limit. Does that make sense? Okay. And okay, we shouldn't blame Riemann for this. Like, the concept of a function in Riemann time was like he would have been bewildered by this example. So okay, but anyway, was there a question? Okay. All right. Third fundamental problem or question, I guess. 3 is the question of length of curves. And these are now related to the second point, I'd say. So if you have a curve in RD, so which is a function from a closed interval AB, I'm taking values, let's just say in R2. If gamma is a C1 function, R2. So an example is like just our mapping from the interval 0 2 pi to the circle is an example of a curve, right? Here's our curve. Here's gamma A. Here's gamma B. If gamma is a nice smooth function, then the length of gamma is just defined to be the integral from AB of the integral of this vector, the length of this vector gamma. I can differentiate gamma, and then take the length of this vector in the plane in this case, and one obtains this by how is this obtained? Well, you chop this into a nice smooth curve. You can chop into ever smaller pieces and just measure the length of these line segments and then add them up, and then the Riemann integral. You take a limit, of course, and then you obtain some Riemann integral, and it's given by this formula. Okay, so that's great. But then you say a curve is like rectifiable if this length is finite. But I needed a C1 curve. I needed the curve to be very smooth to do this, right? I needed it to be C1 or at least piecewise C1, I guess, to make sense of its derivative here, and then measure its length. So it could be a bunch. So I could still measure curves, which are, say, a bunch of different line segments with corners like this, just by measuring finite number of these things, just by measuring each line segment like this and then adding them up. So piecewise C1 curves, maybe we could say, but let's just focus on one piece of a piecewise C1 curve and say, okay, this is the formula. But this seems too restrictive for just measuring the length of something. Like this, it's like requiring too much of the smoothness. So what I want to do is, so another question we want to answer are, what are the minimal conditions on gamma such that L of gamma is finite? So if gamma is C1, that's true, but this seems restrictive for the problem the problem that we're trying to answer, right? And then two, the same question in such that star holds, where this is star, the formula star holds. So what are the minimal conditions on gamma such that it's finite length? And then moreover, what do I need to assume about the curve gamma so that this formula holds for the length? And then implicit in the question too is like how to make sense of this integral if this is not a Riemann integrable function. And there are cases that arise naturally where that arises. And then 4, this is the kind of the highlight of calculus, is the relationship between differentiation and integration via the fundamental theorem of calculus. So what do I mean by this? So for a So this is fundamental calculus is 2 statements. One, that if I have a function f prime that's Riemann integrable, then this integral is given by the difference of the antiderivative of f evaluated at the 2 endpoints. And 2, the derivative d by dx of the integral from 0 to x of f of y dy is equal to f of x. Okay, and the 2 questions we want, so the issue, I guess, is there exists f such that f prime is not Riemann integrable, and what are the, okay, we can ask, what are the correct, what are the right, maybe, assumptions on f such that the formula holds? All right, can we strengthen, what's the is there a natural strengthening of the fundamental theorem of calculus? Can we relax the hypothesis in that theorem? And okay, these are kind of the four main questions at the heart of integration theory, and we're gonna try and answer them. So, are there any questions about these questions? And let me say one more thing, is that like this is kind of a major undertaking, and on the other hand, like we're going to kind of take apart the beautiful theory of Riemann. So anytime you're about to say this theory of Riemann is insufficient, you better come correct with some reasons for doing this undertaking. So so I'm trying to emphasize that this is like, these are important enough questions that we need to try to fix the theory of integration. Okay, so any questions at the outset? If not, I'm going to launch into the Lebesgue's. Well, I'm going to start by launch into Lebesgue's theory, I guess. All right, let's begin. Okay. Okay, so before we talk about integrating something, we're going to start with an even more fundamental question, namely how we measure sets, how we measure the size of sets. And let me just make a few preliminary notations. RD, this is equal to set of all X. D vectors. If E is a subset of RD, then E complement is the set RD minus E. So it's all of RD except for the set E is the complement of E. Where if E and F are subsets, E minus F is equal to all X in RD such that X is in E, but X is not in F. So that's what this this minus means in this context with these two sets. You can define the distance between two sets. So the distance between E and F is the inf over all X minus Y such that X is in E, Y is in F, where this absolute values is just the length of vectors in the typical length of vectors in RD. So we'll also need the notion of open sets, closed sets. So U of RD is open in RD if for every X in U there exists a ball, there exists an epsilon ball B epsilon X such that the epsilon ball around X is inside of U, where this is all Y and RD such that X minus Y is less than epsilon. Okay, and then V is closed if V complement is open. So the definition of a closed set. Closed sets are those complements are open. So a particular set can be neither open nor closed. And then a couple notes about open sets and closed sets. So how they behave under unions and complements. So if a collection are open sets, alpha and some index set A, then the union is open. So openness is preserved under taking unions. even under infinite unions. And closed is preserved under intersection. So if F alpha closed, then this intersection of closed sets is still closed. A set's compact, so K is compact. It's a compact subset of RD if and only if K is closed and bounded. Bounded means it's contained in a large ball. This is a theorem. In fact, the typical definition of compactness is that for every open cover of K, you can refine that cover to a finite subcover. And if the sets are living inside RD with the metric that we've defined, the typical metric on RD, then that's equivalent to the set being closed and bounded. But the main objects we're going to be working with for a while are simple looking sets, rectangles. So rectangles, R as a rectangle is a product of intervals. So A1, B1 times is equal to all X in RD such that for each of the components of the vector lies in between AJ and BJ. The J's component of the vector X lies between AJ and BJ, the interval AJ to BJ. So these look like exactly what you have in mind. Here's A1, A2, A1, B1. So this is an interval in R2. Here's A2, B2. So it's a product of two intervals, and you get a rectangle. In 3D, these are rectangular cube things. Okay, and then the key point, our key launching off point, is that if I have a rectangle, I can measure its volume. So this is the volume of a rectangle. And it's just equal to, well, I take the product of the lengths of these intervals. So B1 minus A1 times B2 minus A2 times BD minus AD. So the volume of a set is the product of rectangles. A cube, Q, is a rectangle with the lengths of the intervals are the same. So L and then the volume of a cube is equal to L to the D. Where the cube there's a fixed side length. So again, nothing in R2, the cube is a square. Right? These words mean what they mean in everyday life. Okay, so our goal is to generalize. So so not every subset of RD is a rectangle or cube, right? Rectangle. Not every subset of the plane is a rectangle, and we'd like to define define a notion of measure of a set, which agrees with the notion of volume of the cube, volume of a rectangle, right? On rectangles. All right. So what properties? So measure. So we'd like to assign a function to sets that generalizes volume of rectangles. Okay, so meaning that so a measure is a function. Let's call it where it takes subsets of RD or the input, and we spit out a number. Right, and we'd like this to be like, let's start with positive measure, right? We'd like, if we're just generalizing the notion of volume of cubes don't have negative volume, right? A subset of the plane shouldn't have negative measure. So let's say this function should be a positive number, non-negative number. So what properties should mu have? And we're just going to try and keep in mind a little bit some of the things that we discussed at the beginning of the class. So I'm going to write down some natural properties that a measure should have, and we're going to discuss whether we all agree. So one, if I have a bunch of different subsets of RD, are either a finite or infinite collection of disjoint sets, then I'd like the measure of their disjoint union, E1 union E2, and possibly going on if it's an infinite collection, to just be equal to the product of their measures, right? The sum of their measures. Right. This is right. If I have a rectangle here and another rectangle here, and they're disjoint from each other, I'd like the measure of E1 union E2 just to be plus the measure of E2. That seems like a benign property to have, and a natural one for the measure of the size of a set, right? If I have disjoint sets, then I'd like the measure to have this additive property. Two, if it's a measure, I would like it to not really care about how the set is, like where I put the set. Like if I place a cube over here, or if I place it over here, I shouldn't change the volume of that cube, right? So if E is congruent to F, naturally congruent, which means like maybe so if I can obtain from E from F by either like translation or applying some rigid motion, then I don't change the measure. E.g. in R, so if I take F to be E plus A, where A is a real number, so equals a set of all X plus A such that X is in E. So if I just take a set and translate it by A, a subset of the real line, I don't change the measure of it. Then the measure of E is equal to the measure of F. So I'd like this measure to have this property too, right? And then three, the third property that I'm going to have, no one's going to fight with me here. The measure of, let's say, the measure of the unit cube is 1, right? If Q is a unit cube, just a cube with side length 1. So 1 times 1 times 1 times 1 times 1 is equal to 1. All right, so these are the three properties I'd like measure to have. And my question is, do any of these seem unreasonable?
I have a question about the first property, I think it is.
Yeah.
So do they need to be disjoint, or maybe you want their intersection to have zero measure?
Okay, so I just disjoint.
Okay, but it would still be the same. Like I'm imagining like you have two rectangles, but they're joined at an edge.
Yeah. Yeah. So I'm gonna ask you. I'm not gonna not will eventually want that to be true. But I'm putting even something even weaker, right? I'm asking for something even weaker. Just I want if they're completely disjoint, then I'd like this to be true, right? So yeah, that's an additional property that you maybe want to have as well, right? But I'm not asking for even that. I'm asking for something. You're right. That does seem that also that seems reasonable as well. But at the moment, I'm not even asking for that. I'm asking for the weaker property that if they're completely disjoint, then I'd like their the measure of their union to be equal to the sum of the measures. So I think the correct answer to this is that I don't think any of these properties seem too unreasonable, right, to have for a measure.
Sorry.
They seem very reasonable to have, and in fact, yes.
Can we add one more property saying that the empty set has measure 0?
Sure. Sure. You'd like yeah. Measure of the empty set is 0. That's an additional property that you'd like, right? I grant that one sounds natural too. And let's add that to our list. So yeah. So but the terrible thing, and this is baffling, is that these three properties are mutually inconsistent. But 1 through are mutually inconsistent. So this is a bit of a disaster. Should yes. Okay. All right. Let's put some explanation points here. So I'm going to show you why they're inconsistent with each other, and let's see if anyone objects to my logic. Not my logic, but the logic I'm going to show you. I'll show you. Okay, so let's suppose we have such a measure on subsets of the real line. Suppose such a measure mu exists. Okay. A terrifying example. All right, I'm going to define an equivalence relation on numbers. So definition, we'll say, we'll write x is equivalent to y, x twiddle y, if x minus y, so for x, y, and r real numbers, we'll define equivalence relation on real numbers if x minus y is rational. Two numbers are equivalent if their difference is a rational number. Actually, let's just do this in the interval 0, 1. Okay, so if their difference is rational, then the claim is that this is an equivalence relation. So claim, I'm going to update my Dropbox file. This is an equivalence relation. y? Well, x is equivalent to x. 2, if x is equivalent to y, then y is equivalent to x, right? So the first one, if x minus x is 0, so that's a rational number. The second one, if x minus y is rational, then y minus x is equal to minus x minus y, which is also rational. And 3, if x minus y is rational and y minus z is rational, sorry, y is equal to z, then x minus z, x is equivalent to z as well, sorry. So you can check all 3 of those. And note 2 equivalence classes. So this is true of an equivalence relation. 2 equivalence classes of numbers I'll call these E alpha, are either disjoint or equal. Right, this is just a property of an equivalence relation. Equivalence classes are disjoint. If you have 2 of them, they're either completely disjoint for each other or equal. You can't have an element that's in 2 distinct equivalence classes. And note that the unit interval is equal to the union of all the equivalence classes. Right, I'm not saying anything, just I've defined an equivalence relation on the unit interval, so I recover the unit interval by taking the union of all the equivalence classes. I've just chopped up the unit interval into a bunch of disjoint equivalence classes. All right. Now let n, then let script n be defined the set obtained by choosing exactly one element from each E alpha. So we're going to form a set n, or you're going to form a set n by just picking your favorite element from each equivalence class, E alpha. So n is equal to the set of all x alpha. And our ability to do this is called the axiom of choice, which is just the statement that we can do something like this. Choose an element from each, choose a representative from each equivalence class. Okay, so now we're assuming we have a measure on a measure satisfying the 3 very natural properties that I wrote down on a few slides back on the unit interval. So my next thing I'm going to do is now so next enumerate the rationals in 0, 1. So no, sorry, in the interval -1 to 1, I guess. So it is look at the subset of the rational numbers intersected with the interval -1 to 1. And since this is a countable set, the set of rationals inside 0, 1 is a countable set, countable means I can put them in a list. So put the rational numbers in a list, index them by k natural numbers. So R1, R2, R3, R4, R5, those are list all those rational numbers. And now consider the translates of the set n given by nk is defined to be the set n plus rk, plus the rkth rational number. So you just take the set, you pick rk, I give you n, and then you shift it over by rk. Or shift it to the left or shift it to the right. Okay, so claim. I'm going to claim two facts. One is that the interval 0, 1 is a subset of the union. I don't know why I write union like that. The union from k equals 1 to infinity of the nk. And moreover, that this is inside the interval -1 to 2. Okay. And 2, so this is the first part of my claim, and then 2 is that all nk are disjoint. Okay, let me prove this claim. So for 1, it's clear, since I'm just shifting by a rational number that's between -1 and 1, and all my elements of n are within 0 to 1, that I can't get anything bigger than 2, and I can't get anything bigger than -1. It's clear that for every k. So now, so let's prove that. So that takes care of this inclusion, right? I just translated. Now the claim is that the unit interval is a subset of this union. That's a little trickier. So now let x be in 0, 1, and I want to show that x is in the union of all this union, right? Somehow. So x is in 0, 1 implies that x is equivalent to x alpha for some alpha, right? Where x alpha is the representative I chose from, or the x alphas are the representatives I chose from each equivalence class. So since, right, the union of all the equivalence classes is the unit interval, there's x is equivalent to some x alpha. That means that for some alpha, that means x minus x alpha is equal to rk for some k, right? It's in the same equivalence class, so it's equal to some rational number. And the rk's are drawn from -1 to 1, so we're good here. Which means that x is in k for some k. Right, because, yeah. And this means that okay. This is because x is equal to x alpha plus r to the k. Okay, so that takes care of 1. Now let's prove that all of these nks are disjoint. This I can do by hand. So suppose nk intersect nk prime is not empty. Then there exist rationals rk not equal to rk prime, and suppose that these are not the same set. Okay, too. And alpha and beta such that x alpha plus rk is equal to x beta plus RK prime. Right, this is what it would mean for these two sets to be not disjoint from each other. Then they have a common element, and the common element can be expressed in two ways, right? One like x alpha plus RK, and another way by x beta plus RK prime. But now I can just subtract on both sides. This means that x alpha minus x beta is equal to RK prime minus RK. RK, they're both rationals, so this is a rational number, which means that the difference between these x alpha and x beta is rational, which means they're not in disjoint equivalence classes. This means that x alpha is equivalent to x beta. And this is a contradiction. Okay. So these two properties hold. The union of the NKs are between are contained in the interval 0, 1 and are contained in the interval -1 to 2, and they're all disjoint. Wonderful. And remember, now recall, NK is equal to N plus RK, which means that the measure of NK is equal to the measure of N, right? Because all I did is took the set N and shifted it over. So this means by the property 2i, the 2 of the measure, the natural property they should have, this should be the same by 2, by property 2. But since they're disjoint, is a disjoint union. We have one, and it's contained. It's a subset. Is a subset of -1 to 2, the interval -1 to 2. If the unit interval has measure 1, this should have measure 3, right? The interval from -1 to 2 is 3 units of length, right? So I'm using this, and I'll use this as well. So this set sits in between these two sets. So its measure should be bigger than 1, right? What am I doing? And it should be less than 3, right? But these are disjoint, so by 1, this is equal to the sum of the measures of the NKs. Which is equal to the sum of the measures of, this is by 1, sorry, this is by 3. Which is just equal to the sum of the measures of the set N. And so now I have 1 is less than or equal to the sum from K equals 1 to infinity, the measure of N, which is less than or equal to 3. I have a set N which would have this property. So, but this is now impossible, right? This is impossible because this is an infinite sum. This is impossible, and I'm just summing the same thing up over and over again. Since either the upper bound implies that the measure of N is equal to 0, right? But the lower bound implies it's not equal to 0. Both. by the bounds above, right? I can't add up something infinitely many times and have that be bounded, right? There's no way, right? There's no way to do this. Okay. All right, so we're done. That's it. We should just wrap it up, right? Yeah. Some people never get over this. Maybe someone in this class will never get over this. In fact, there are math faculty at prestigious universities who have never quite gotten over this example, and so they claim that they they claim that they can just do their job, like a 9-to-5 job, where they accept that this example is there, but then in their private lives thinks that everything they do during the day is just complete nonsense, basically. So this seems kind of awful, right? Because these three properties that I wrote here seem very natural. Nothing seems out of place, and nothing that I did seems too weird too, except for one step. So okay, so let me make one caveat. So no one objected in one that I made this requirement about an infinite like this. So one thing you could say was, well, maybe this is too much to ask. That I require this property hold for an infinite collection. Infinite sounds bad, and maybe this is too strong. Well, it turns out that even with just requiring that finite disjoint unions have this additive property, is also leads to paradoxes. I can discuss in a minute too. So one thing you could say is, well, let's just scrap property one I, or weaken it to say let's only require finite things. So I claim that leads to bad things too, and then I also claim that like once we do that, then we're not going to come close to answering some of the questions that we started off with. One of the questions we started off with was about limits of sequences of functions converging pointwise. If we don't have a mechanism to deal with like infinite stuff, then what are we doing here? We're certainly not going to be able to do calculus. So I really do want to keep this like infinite collect, or this property I. So the second remark is that that you might ask is did I do something fishy here in the proof that I so confidently wrote down or copied down here from my notes? And the thing that I think the only thing that's kind of eyebrow raising was this step where I was like, now choose an element, exactly one element from this infinite collection of sets. Just choose a representative. And this sounds fishy. I mean, like this axiom of choice, the fact that I needed to call it an axiom might sound fishy. And it is kind of fishy. So let me describe a bit this axiom of choice business. So so what's fishy here? No offense to fish. So the axiom of choice was used, and this is the thing that I was referring to when I said some people are just not comfortable with this in particular, because allowing it leads to so many weird things. So the choice is used. What is choice? So what is this? So if E is a set, E alpha is a collection of non-empty subset of E, then the axiom of choice says then there exists a function. Alpha tends to is associated to X alpha, the choice function. So the axiom of choice is there always exists such a function. If you give me a family of non-empty subsets, then I can pick an element from each of the subsets. I can choose. There exists some function, a mechanism for me to choose. And the axiom of choice goes hand to hand with something called the well-ordering principle. The well-ordering principle, which is the same, so if the axiom of choice sounds funny to you, maybe you'll like an equivalent notion called the well-ordering principle. So I claim that the axiom of choice is implied by this well-ordering principle, and actually vice versa too. So the well-ordering principle, so a set has a linear ordering. So if E is ordered, the real numbers are ordered, a linear order is A, and X is less than or equal to X. B are distinct. If these are distinct, then either X is less than Y or Y is less than X. And C, if it's transitive, if X is less than Y and Y is less than Z, then X is less than Z. So that's what a linear ordering is, and a set is called well-ordered. E is well-ordered if every subset has a smallest element. And the well-ordering principle is that any set can be well-ordered. Okay. And it turns out that, so you can see that the well-ordering principle, it's easy to see that this implies the axiom of choice. Because you can now, your choice function is just the smallest. You just take, you give the set a well order, and then you choose the smallest element to be your choice of the element in each subset. Sorry, was there a question?
Sorry, just a typo. X smaller than or equal to Y and Y smaller than or equal to Z.
Sorry. Yes. Thank you.
Does there have to be some restriction on like finite subset or of the integers or something? Because as written, like wouldn't like 1 over n, like not every subset has the smallest element if something like converges to a lower bound.
So what you're saying is this sounds super weird to you.
Yeah.
Right. Good. Most people lie in two camps. It's like one of those things where you either see the like what the dress is like. What was it? It was your orange or blue or something like that. So either the well-ordering principle sounds bad to you, or the axiom of choice sounds bad to you. I think the well-ordering principle sounds weird, but the axiom of choice sounds supernatural. Other people feel the opposite. The well-ordering principle sounds natural, and the axiom of choice sounds fishy. I think it's good. I think it's good if some of this sounds a little fishy, because it leads to some paradoxes. But on the other hand, like it's kind of hard to go on without it. So, um, so maybe just like maybe Andy, a good thing for you to do is just think about the axiom of choice, like and like forget in my head. I think I forget what the well-ordering principle. I think I like just lobotomize myself every time I like have to read what the well-ordering principle is, and because it makes no sense to me, um, and and then I just remember the axiom of choice, which seems okay. And then so people were like, "Oh, do you believe in the axiom of choice?" I'm like, "Yeah, sure. That sounds fine." So yeah, these are this is okay. That's the point. So this is kind of the point. Is that the well-ordering principle implies the axiom of choice. One can in fact also show the opposite, that the axiom of choice implies the well-ordering principle. So if you like the axiom of choice, I'm sorry, then you have to live with the well-ordering principle too. So that's the this is the and like I was saying, there are just some very mathematicians, in fact, who are just like, this is all nonsense. And if you press them, what they'll say is they like, I just don't believe in the concept of the infinite. So just like say, well, we're sort of just saying that there's a very large number of things, and the infinite just a very large number of things. A lot of probabilists actually talk like this, even though probability theorists like work with real numbers and measure theory maybe more than any other group of mathematicians. Okay, so go ahead.
What do you lose if you do not use these principles in the analysis?
If I don't use which property? Sorry, it cut off real quick.
If these axioms are fishy, what will we lose if we do not apply in any proof?
I see. So quite. So I'm having trouble thinking of a good example off the very top of my head that's accessible. But there's a bunch of stuff. The answer is quite a lot. There's something called the Hahn-Banach theorem, which is pretty fundamental, which is gone without axiom of choice.
Maybe the theorem is Fisher too. Then, so why people insist?
Yeah. It's excellent point. So some people just like it is an active like sub area of mathematical logic, I think, to create an axiom system where you can. So the problem is that you have trouble doing even like calculus, or you basically lose all of modern mathematics without the axiom of choice. And I guess that's the key the key issue. Not just modern mathematics, but like all of 20th century mathematics without the axiom of choice. It's kind of implicit in almost everything that deals with the infinite. But like you're saying, it does seem a bit fishy, right? Or there is some fishiness to it because of like the examples that I just wrote down. I'll write down one other example. I realize that we're out of time also, so maybe we're going to stop here. But I'll start with another bad example next time. But so people do this. People try to create axiom systems where they can try to recover mathematics without the axiom of choice. But it's largely been an unsuccessful endeavor. And so most people just kind of hold their nose and just allow for some of these paradoxes. And I'll tell you how we're going to fix the paradoxes in a second. Is that the answer in our context is going to be that we're just going to not try to measure all sets. We'll just say some sets just aren't measurable. And that is like so that's the bit that that most mainstream mathematicians live with, is that we just can't measure all. We can't define them. The biggest fix to the problem we just created is that maybe this funny set that had these weird properties, we should just discard that from the collection of sets we can try and measure. And the point will be that we'll be able to do good enough without those sets. We'll just have to accept that some sets are not amenable to this. They're kind of pathological. The set that I created was weird, right? I used the axiom of choice to create the set. So that's the answer. But the big part of your, like, from what I understand, I'm not an expert in this, but by any means. But from what I understand, that it's very difficult to do any modern mathematics without the axiom of choice. At some level, it's there lurking. Okay. No problem. Good, excellent questions.
Quick, how does the axiom of choice imply the well-ordering principle?
I don't know off the top of my head. Yeah. It does, I know, but I just I'm not close to being an expert in this business, so I couldn't even. I don't think I should even try. Maybe I wonder if it's in the book. I'm not sure. So it might be in the book, but I see from Michael. Learned it in 5:10, and the proof was quite hard. Okay. Sounds like something I wouldn't know. All right, guys. So I'll be in my office hours in a couple minutes. So if anyone would like to come there, we can continue the discussion. Okay. Bye, everybody.
Thank you.
Thank you.
Thanks.